Hey, Sandeep.
Hey, hi, how are you doing?
Yeah, good. How about you?
Good, good, good. Everything is going well.
How's the weather in Toronto right now? It's getting cold in Vancouver.
What is it?
Yeah, I mean, slightly, but better than a couple of weeks back.
Recording in progress.
It's quite warm here as of now. Okay, it's quite warm. It's raining. It's going to be raining now for a couple of days. Let's see how it goes. All right, how is everyone?
All good,
Yeah,
Sandeep.
all good? Okay, so how many of you have actually looked at the gradient descent, the one that we did last time? Okay. Did you try to explain gradient descent to somebody? It's a brilliant exercise. If you try to explain gradient descent to somebody, it is going to be awesome. Okay. All right. All right. Shall we start? Did anybody code it yet? Yes? No? After our last discussion? Okay.
What code are we talking about?
The gradient descent?
Oh, no.
No? All right. All right. Great. Great. So far we discussed the basics of things, and yeah. And we also talked about the gradient descent. It's it's very, very important for everybody to get full control of it. It's a pretty simple thing. In our normal life, we actually do such kind of things really, really often, and we basically do it really effortlessly in normal life, right? If you have to go somewhere, or let's say you want to put a thread through a needle, right? So you will hold the needle, you will put an effort in it, and then observe how far did you land up, and accordingly you will keep tweaking your direction until you get the thread in the needle, right? So that's kind of the game it is. So you basically have these weights or knobs. You basically tweak those knobs until you get the desired result. Okay. So it's a very important phenomena, whether we say generative AI, creative AI, natural language processing, computer vision, everything is about optimizing the weights in order to get the desired prediction. Okay, that's the core idea. All right. So I would just take the look at the presentations. Yeah, this is the one that I was talking about last time. And basically, right, this one, okay. So basically, the machine learning has two phases. One is called training and other is called prediction. In training, what we do is we have a historical data. We feed it to the algorithm. Algorithm looks at the data and comes up with the model, right? In the case of linear regression, what was our data? Our data was, right? The data was looking like this. This was one data point, other data point. Now, using the algorithm, we came up with the model, which basically was this line going through the data. Okay, so the algorithm looked at the data, came up with the model, and then once we had the model called straight line, given a value of any of this x value, when we have the model going through this data, now given the value of x, we can predict y, correct? You give me any value, I'll ask this line, what is the value of y for this value of x? And that's it. Okay, so I'm just giving you a very simplistic example. And that's the core of the entire thing. All right. Like, for example, when we are predicting salary, right? So we can quickly say, looking at this number, the next number is going to be 8,000, right? And so the salary is essentially the historical data. And the x-axis, the variable, is our years of experience, and the salary is our y. This is x, this is y. We want to predict salary given years of experience. If we had to predict the years of experience given the salary, then this will be our x and this will be our y. All right? So keep that in mind, that nomenclature of x and y. Y is something that we want to predict. X is something that we want to input. Okay? In case of ChatGPT, our X is the input that we are providing, the prompt, and Y is the outcome it's giving, that is the answer, right? So given the historical data, we train the model. Once model is ready, then we give the year of experience, it will give the salary, right? I hope this diagram is clear to everybody. Yes? No?
Yes, yes.
Okay. Now, how would a computer do it? Computer would take 2 points or these data and come up with this graph or some strategy to predict the outcome, right? That's how it'll do. Let's say we are given these 3 salaries for first year, second year, third year, and we plot the graph through them, and given the 4th year, it will predict the value of y. Okay, now that was easier to do, but if our data is like this, my first year salary is, first year salary is per month $2,000, then $3,980. Then in the third year, my per month salary is $6,020. Now, what will be my exact salary on third year, right? This is where what we do is we try to draw a line through this data. This is called linear regression. Linear regression is one of the strategies. We draw the line through this data and try to see that the prediction is should be accurate, right? As per our line, for years of experiences too, this is the predicted value, right? This is our predicted value. This is also our predicted value for line in the years as 3, years as 1. What is the predicted value? This is our predicted value, correct? These are 3 predicted values for those 1, 2, and 3. Correct? Everybody okay with this? No?
Yes.
Yes, yes, yes.
Yes, Sandeep.
Yes. So how do we find that line which has these 3 things really small? Okay, really small. How do we do that? One strategy could be that we iterate using a for loop. We basically start drawing all the lines and keep on doing that. One strategy is that. And the second strategy is to go a little more greedy way, or you can say sensible way. And how do we do that is using the gradient descent, right? There could be infinitely many lines that can be drawn on 2D graph. And this is where the gradient descent that we have talked about earlier comes in. We draw a random line. In the beginning, we make a guess of slope and intercept. Intercept is what? What is an intercept in this diagram? Yes. The intercept is,
Difference between prediction and actual.
this is intercept.
Okay, sorry.
Okay. Y equals mx plus c. When x is 0, the value of y. This is intercept. Okay. So where like these lines have same slope but different intercept. Okay. Got it. They have all same slopes but different intercept. Got it. Now here is an interesting part. So what we do in gradient descent is that we take an initial guess, a random guess, just draw any line. And then we try to lift it a little bit, meaning change the slope a little bit, increase the slope a little bit, tiny little bit, 0.001. Okay. Observe whether increasing the slope did a good job or bad job. Observe the rate of change of error, rate of change of error with respect to the rate of change of slope, and then accordingly make a jump. Okay. If the next line, if it is reducing, lifting this line is reducing the error, we increase the slope. Otherwise, we decrease it. Okay.
So
Now,
error, sorry, Sandeep, to interrupt. So error we calculate using the same thing, right? Where we square the deviation and then
yes.
sum it up.
These length that you see, we basically square all these lengths. Okay.
Yes. Thanks.
And yeah, but you can come up with all kinds of error functions. Somebody suggested to the power 4, somebody said absolute value, somebody said somewhere between absolute value and mean squared error. You can try all kinds of things. Okay. Now, let's move on. Here, what you see is, right. So here is the formula for guessing the change in slope. So how much slope should we increase, right? Earlier, our slope was this much. Now it is this much. How much should we move? So people realize that multiply by some constant called learning rate, where to the rate of change of error with respect to change in slope. How much did how much error was decreased because of increase in slope? This is increase in slope. Increase in slope. If the error did not decrease, right? So if the error did not decrease, instead it increased, so this will become negative, right? So how much should we increase the slope? Some constant multiplied by the rate of change in error. Is everybody okay with this formula? No? Yes?
Yes.
Even if you have not attended any of my previous classes, this should be clear to all. Yeah, please, if this is not clear, please stop and ask right away. Okay.
Sandeep, can you explain it once more?
Yeah. So see, basically, what we're trying to do, we want to draw a best fitting line, correct? How would you do the best fitting line through these 3 data points? Okay. Visually, yes, as human, we can do it, but using computers, how would you do it? One way is try all possible lines, right? Which is not really possible even for supercomputers, right? Instead, do a little bit more greedy approach. Okay. We increase slope a little bit, observe, did the error increase or decrease? If the error decreased, keep increasing the slope, otherwise just decrease the slope. Okay. So question is, how much should we increase the slope? So our next value of slope should be somewhere proportional to rate of decrease in error with respect to change in slope. Meaning, by increasing a little bit of slope, if we got a good value in return, our return on investment, you can also think of it as a return on investment. Okay, ROI. We put a little bit of investment, we got a good one. So we should take our next step in proportion to how much returns are we getting. Okay, is this clear?
This rate of decrease of error, this learning rate will be always the same. Like we will fix that learning rate. Is that so?
No, that's some constant. Okay.
Its constant is very small.
You usually, people have figured out that if you put it like 0.0, right? This is learning rate, right? This is learning rate, 0.01. For some people, this is the successful. Some people say, okay, use this. Some people say use 0.002, right? So you can also observe, it doesn't make much of a difference, by the way. I'll talk about it. What difference does it make? Okay. If it is too high a value, then it becomes a troublesome, right? What happens is, if this learning rate is, let's say 20, okay, what will happen is you will, right? You observe that, oh, increasing this basically decreases the error, right? So you draw a big line, okay? And then now, when you are increasing it, it says that, oh, you're going too far, come back. Now, next line you'll draw is somewhere like down. And therefore, you'll keep on diverging, right? Therefore, you want to keep this small. If your error is not reducing and instead error is increasing as you are trying more, you must bring down your learning rate. Got it?
So learning rate, I mean, how do we derive it? Means I believe we are going to learn it, but so I mean, whatever learning rate,
it's a random constant.
random
Okay.
constant. Okay.
It's usually people keep it like 0.02, 0.02, not 0.002. Okay, that's the value that people keep. Okay, 0.02, that's what people figured out. But the thing, the rule of thumb is, if when you are trying again and again, increasing the slope and moving the line back and forth, if the line is, instead of converging, instead of error reducing, if the error keeps on increasing, right? That means you have to bring the learning rate to be smaller. Like, for example, if, let's say, next guess, instead of being this line, if the next line was this, okay? And after, when you again try, the next line turns out to be somewhere like this or somewhere like this, right? That means you are going away. You're going away. Okay?
But
But then why
Sandeep,
do?
sorry,
Mhm.
sorry,
Sorry,
on that, right? Why would we change the learning rate? Because if the rate of decrease of error with respect to change in slope, if that is negative, which means that the error is increasing, then the increase in slope will become negative, right? That means that the increase in slope should be negative, so it should be decrease in slope. So why would we change the learning rate in
No,
that case?
so see, the thing is, we got, okay, rate in increase in, we are saying First of all, one way could have been that, okay, we basically increase our slope by fixed amount, let's say 10 degrees, decrease or increase by 10 degrees. That doesn't make sense because every time we see the profit, okay, because of increasing the slope, essentially we have to, first of all, what we are trying to do, we are trying to come up with a line that is best fitting, right? Now, there are ways to derive to a point where we get the best fitting line, but that is a very intensive process and requires a lot of more computing. A easier thing is to do a hit and trial. How do we do a hit and trial? We increase the slope a little bit, observe if the error decrease or not. If error is decreasing, the rate of error is with respect, the rate of change in error with respect to change in slope, right? Okay, this is how we symbolize, or you can say delta E by delta M.
But
Delta
then
E,
why can't we simply eliminate the learning rate from the equation?
okay, so you are saying that this increase in slope is equal to rate in decrease in slope, right?
Yeah, means
So what if that is going very slow? Like your next line comes like this, then you again increase, it comes like this, then you again
So
increase, it comes like this, and and then there.
So basically, the learning rate is the step which we'll be taking, right, on the
Yes,
positive or negative side.
yes.
But for so understood. So for a given scenario, we'll not be changing the learning rate, right? We will be changing. I mean, we won't constantly keep on changing learning rate. We'll take a learning rate and then fix it for our experiment,
Correct.
right?
Yes, yes. So the only thing you have to keep in mind, if your error is not dropping fast, okay, just increase your learning rate a little bit. Okay. If your error is just jumping, it's increasing rather than decreasing, every time the error is increasing, then that means you are jumping too much, right? Instead of next line being this, you drew this line. And then instead of coming down, down here, you came down here. And then instead of increasing it, you went up, then down. So basically the slope is just jumping back and forth. Got it. If the learning
Understood.
rate
But
is too high.
Understood, but once we realize, and as you said, right, with a lot of trial and error, it's been said that it should be somewhere between 0.001 and so on, right? So
Yeah.
if we take that,
Mhm.
our iteration of testing and working on a model, that
Yeah.
iteration we don't change the learning rate, right? We keep that constant.
Correct. Correct. Once you have figured
Okay.
out that this is good enough learning rate, then you basically train your
Okay.
model.
Okay.
Okay. Our purpose is not about finding learning rate. Our purpose is to find the best fitting line.
Got it. Now, on the best fitting line, sorry, my earlier question, right? Will there be a negative? There can be a negative rate of decrease of error, right? And that
Yeah.
will,
If
means that will give you a negative slope, negative increase in slope, which is decrease in slope.
yeah, like here, tell
Okay.
me this. Tell me this. Here, what do you think? This here, what will be this? Positive or negative? Rate of change of error because of increasing slope is negative or positive?
It will be positive here.
Rate of increase, will the error increase? Okay, let me put it this way. If I increase slope, will the error increase or will error decrease?
Error will decrease. Sorry.
Error will decrease, right?
Decrease. Yeah.
Correct. That means that rate of change of error with respect to M is negative. Correct?
Yes.
Is everybody clear about this? If I increase the slope, error will decrease. You see, we can see from the data that this is our line that is fitting, which has higher slope
But
than this line.
but Sandeep, in the formula, we are not using the rate of error, right? We are looking at rate of decrease of error, which means that we'll have to take the negative value, right?
Yeah, this is equal to minus of rate of change of error divided by
Okay,
rate
got
of
it.
change of
Yeah,
yes.
got it.
Okay, meaning when we slowly test, okay, we are saying minus E2 minus E1 divided by M2 minus M1, right? Before trying it out, whatever was our slope was M1, we increased the slope to M2. Earlier the error was E1, then error became E2. So if the error, right, because of increasing the slope, if the error is also increasing, we don't want it. We want opposite of it. We want to go in the direction where error is decreasing. Correct? Is everybody okay? Or have I confused you thoroughly? No?
Okay, but I think I have
Ask.
to again.
No.
I have to again.
Ask now. Ask now.
No, not now. Just where I think I need some time to grasp again, kind of absorb everything.
Okay,
As such, it looks straightforward, to be
okay.
honest, right? Because
Okay.
and kind of
Yeah.
obvious as well.
Okay. Then try saying it now, what you understood, whatever you've understood.
No, so it's basically what we are doing is we are changing the slope, right? And then like we are increasing the slope, and then for every increase in the slope, we will calculate the error,
Yes.
right?
Yes.
And then based on that, and the learning rate has to be a very small constant.
Yes.
And right. And so based on that, we will know whether we have to go up, increase the slope further, or we have to decrease the slope from that point.
Correct.
Is that correct?
Yes. Yes.
Sandeep, you said that there is a negative, right? Negative of delta E by delta M.
Yes. Yes.
Why we are putting negative there?
Basically, see, let's say, take a look here. Okay. Here, let's say initial was M1 before when we were trying, right? This is, let's say, M1, this one, M1, and this one is M2, correct? And for this line that you see dashed as the dotted line, the error is E2 and error is E1, correct? Okay. So, in this case, right, M2 is greater than M1, that you agree? Correct?
Yes.
Do you think E2 is greater than E1?
No, it will be negative.
Correct?
Yes.
So if you see delta E by delta M is negative.
Yes.
Okay. So what we want is, we want this thing to be negative, correct? We want to go in that direction where rate of change of error with respect to M is negative, right?
Okay.
Okay. We want to focus on decrease of error with respect to increase in slope. Okay. The delta E by delta M is increase in error with respect to increase in slope. Correct? So, how much should we take the next step? In proportional to how much return on investment you got in the previous step, right? How much return on investment we got? We got the investment of minus of delta E by delta M, right? Minus, you see? Because if you don't put the minus, it will be increase in E with respect to this. Okay? Now, if this turns out to be positive, right, what will happen? We are going to put a negative sign in front of it, and that's how we will come down. The slope will become negative. The change will drop down the slope. Got it?
Oh, okay. Got it.
Okay. So new slope. Okay, let me show you the next formula. I think next formula will make it much more easier. So new slope is equal to old slope plus some learning rate multiplied by rate of decrease in error with respect to the slope. Correct? We can also say, let's say this was our m dash is a new slope. Old slope, let's say this one was, let's say m. This is our m dash. M dash equals to m plus some constant, let's say 0.02 times, right? Delta E by delta M, and we want to do negative. Okay, if this thing is positive, right? If this thing is positive, that means if this thing is positive, what does it mean? If this value is positive, it means that because of increasing the slope, error is increasing. Therefore, we have to decrease the slope. If this is negative, what does it mean? That because of increasing the slope, error is reducing, right? And therefore we need to increase the slope. Now this formula is clear to you?
Yes, Sandeep.
Delta E means rate of change of error with respect to rate of change of M. Okay? Is everybody okay?
Right.
Yeah.
But at some point, Sandeep, if we suppose we increase the slope and then we said, okay, the error rate has also increased. And like first time we increase it.
Yeah.
Okay. So, yeah, no, got it. Sorry, I got confused.
Got it?
Yeah.
Got it. Okay.
Hey, Sandeep, so just one point. When we are saying rate of decrease of error, so
yeah,
there will be some constant, some value where we are seeing whether this value is reducing or increasing, or how are we going to identify where?
Yeah, rate of decrease in error. Error is this length, right? How much this plus this plus this. That's our error. The total of all the errors.
Okay.
Okay. And this here. Okay. This total is what we are trying to minimize.
That will be our error.
Yes. So we want to keep that as minimum. So we observe that, okay, we increase a little bit, again, measure how much is this, compute whether we decrease the error or increase the error. If we decrease the error, just increase the slope, otherwise decrease the slope.
But
Okay.
there could be multiple slopes or multiple lines with the same error rate, right? I mean, suppose, hypothetically speaking, like over here, correct?
Yeah. So see, somebody could choose this line to start with. Okay. And then they will increase it a little bit. They see, oh, error is increasing, so they will bring it down. And that's how they'll keep on trying. Again, they will try increasing it and then see, oh, it's decreasing. It's increasing the error, so go the opposite way. Now it's okay. Now again increase it, and you find that, oh, then there's no change. So you just keep it there. And so you keep on trying over and over the same thing.
No, I know. No, what I'm asking is for the set of data that is given or the set of points, there could be multiple lines with the same error rate.
Same error, total error, right?
Yeah, total error.
Yeah, there could be, definitely there could be. So like, for example, there could be one line, there could be another line, right? There could be definitely. So there could be multiple models.
Multiple models, yeah. Okay.
There could be multiple models fitting the same data.
Same data.
Yeah. Okay. Just having tiny bit of differences. Okay. All right. Okay. All right. The same thing explained again. So if your initial guess was, let's say this one, you tried increasing it a little bit. You just increase the slope a little bit and observe, oh, the error has increased. So you go back, bring it down. And that's what you keep on trying. So you start with the random line, increase the slope a little bit, calculate the change of error. Did the error decrease? Yes, increase the slope. If the error did not decrease, instead error increased, decrease the slope. Okay. And then if error did not change, you have found the best line. Perfect. Is everybody okay? But usually this doesn't happen. You just have to observe that in a couple of iterations, we are just roaming around the same error, and we basically need to stop.
Yeah, yeah. Because the error ideally means for two different lines, it would be very, very rare, right?
Yeah. You will
The
never
normal
get the error
yeah,
equal to zero.
zero. Yeah.
You will never. If you get error equal to zero, okay, there is a high chance that you have memorized the data. Okay. All right. So this is what you keep trying and you keep. Okay. This is another analogy. I want to spend more time on gradient descent. Okay. It's something that I want everybody to understand. Okay. So because mechanics of number of iterations, all of that revolves around the core of the algorithm. Core of the algorithm is mostly everywhere. As of today, each and every part of the machine learning uses the gradient descent. Okay. Therefore, I want to spend more time. Now, here's a tap analogy that you are in a new hotel. You don't know which way is the cold water and hot water. What you do is you increase the you basically twist the knob to one side. Observe that did you get the better correct good water, or the water became worse, right? If it is going in the good direction, then you basically keep moving it further. Otherwise you do it in the other position, opposite one. So you slightly twist it and you observe, oh, it's going too cold. So you go into other direction. Okay. The most important part is observing the change. Okay. Observing the change. You slightly modify and say, okay, earlier the temperature was like this. Now the temperature has dropped. Therefore, let me just try something else. Okay. So this seems to be comfortable position. So we stop there. And when you find the comfortable position of the knob, you mark it on the wall saying, okay, this is the position of the knob that is the most comfortable for me. And you call it your model. Next day, when you go to the bathroom to take bath, you just twist this immediately to the position which you have marked and then start taking the bath. So this is called inference phase, or you can say putting the model in production, right? Because you already have the model in place, you only have to load it and run it. And that's what it is. So when you mark your first day, it took you some time to figure out that sweet spot. And once you have figured out that sweet spot, you have marked it and you call it your model. And then next day, you just go to that sweet spot and start using. So inference phase is easier. Training phase takes a lot of hit and trials. Is everybody okay?
Yes.
No?
Yes.
Now, in the same way, if you have two knobs and you want the good flow as well as good temperature of the water, yes, go ahead. Somebody raise the hand.
No, that was by mistake, Sandeep. That's me, Chandra.
Okay, Chandra. All right. So what if you had two knobs? Okay. Two knobs in the bathroom. You don't know which one is for what. Okay. All you know is that there are two knobs, and all you want is good temperature and the flow of the water. So you increase this, you twist these knob one at a time. So initially you just randomize them. Okay. and slowly increase one of the weights slowly, one of the knobs, and then you observe whether you're getting good flow or your flow is and temperature has improved or not. If not, you keep twisting them. Okay, so that way you basically tweak one knob at a time and observe that, and then change both of them, and then try again and again. That's what you do. Okay, now in a situation, there could be lots of input features, right? It could be, instead of you taking bath, in case your wife is taking bath or children is taking bath, or what is the climate outside, which country you are living in, and how much is the hot temperature and how much is the cold temperature. So you would need more knobs to control all of that. So you can convert this whole problem into an information system. Given the temperature of hot water, cold water, country, gender, and climate, figure out those weights for which you get good flow and right temperature. Okay, so you can basically just come up with more and more knobs and control it. All right, is everybody okay with so far the analogy of knobs?
Yes. Yes, Sandeep.
Perfect. Perfect. All right. So the next idea is decision trees. We'll go into decision trees later. Okay. And for now, I think we'll stick here. Yeah. Everybody is on the same page so far? Yeah.
I have a question. We are talking about slopes, but we are not talking about intercept. So how, when we will also
Okay.
think of intercept?
Good point. Very good question. So question is, we talked about slope here, right? And I did not mention anything about the intercept. Correct. So what you usually do is, at this point, right, the way you increase the slope a little bit, similarly, you will increase the intercept a little bit, just a little bit. Okay, so let me just draw it, and then it'll make more sense to you. So where are we? Let's say this is my data, right? This is my data. Okay, so initial line we drew like this. Okay, first we tweak the slope, observe the rate of change of slope, and kept it aside. Then what we did was we lifted it a little bit. Okay, kept the slope as is and lifted the line a little bit. Okay, we increased the intercept, right? Remember, there are two weights in the line. When we are drawing a line, there is mx plus c, correct? M and C. So first we tried increasing M a little bit, observe the error, and then we tried increasing C a little bit, just a little bit. Okay, for the same slope, we drew another line and then observed, did the error increase or decrease? Okay, if the error decreased, right, based on that, we will basically compute the new value of C, okay, some constant, okay, similar to what we did earlier. Okay, so new value of slope was equal to old value of slope minus eta times delta E by delta M. Okay, this thing is delta, means rate of change of error with respect to M, return on investment. Similarly for the slope. So we basically tweak both of them in the same strategy. Got it?
So when one error is constant, then only we will do the other one, or we can do tweak both at the same time.
We will tweak parallelly, on one end, we do the rate of change of error with respect to M, and the other hand, we do the rate of change of error with respect to C, and we compute both of them and then update C and M together. Okay, and that's it. We just keep on doing that. Okay. All right, first compute both the errors, compute both the new values, and then assign. We never do that first modify M, then modify C, then modify M, then modify C. No. Instead, compute the new value of M and compute the new value of C based on the old value of M, and then change both of them together. Okay.
Sorry,
That is
the process or the computation to change the value of C is also the same, right?
yeah.
New C is equal to
Yeah. So same
okay.
way. So M dash equal to M minus eta times delta E by delta M. And similarly, C dash equal to C minus eta times delta E by delta M. Okay. Once we computed this, what we do? M comma C equal to M dash comma C dash. Right? Is everybody okay with this, or does it sound too alien?
Eta is the learning rate, right?
Yes, eta is a learning rate, correct. Eta is a constant. In simple words, the new value of M is M minus M time plus some either decrease or increase based on whether error is increasing or not. If the delta E rate of change of error with respect to M is more, we tweak M more. If it is less, we tweak M less, like that. All right. I hope this is clear, everyone.
Yes. So basically, the new M dash and C dash will always go up or down in the same proportion.
No. In their own proportion. If you notice this, M dash equal to M minus eta delta E by delta M. Okay. C dash equal to C delta E by delta C.
Oh, delta C. Okay. Sorry.
Yeah.
Got it.
Rate of change of error with respect to with respect to the C. Got it?
Yes.
Okay.
So again, so when we actually do the change, or when we ask, when we automate this change, it simultaneously does both, and then there's a lot of iteration to actually get the final values, right?
So we don't update the value. It's not like we first update. We do not do this. Okay. We don't do, okay, we updated the value. No. Once we computed both new values, then we, in a single shot, we update the new values. Got
Yeah,
it?
but that means millions of calculation, right? Because to get the error rate itself is going to be big, right? If you have a large data set.
Yeah. So a lot of computation there. And this is why NVIDIA is making money. Okay. But yeah, having said that, you will find it that it's not a big deal for normal work. If you are training your most of 99% of the model that you'll train, you can train them on CPUs. Okay, you don't require GPU. Okay. So you should not have an excuse saying that, oh, I did not have GPU, therefore I never trained a model. Okay. And therefore I'd never learned how to train a model, and therefore I never learned how to do gradient descent. Okay. Okay. There is no point in learning gradient descent just because I don't have a GPU. Okay.
Damn, that was my one excuse when you just saying that.
No, I have heard these excuses in my company. Okay. So, like I remember in DevRev, some senior guy said, "Oh, but how will we train the model? We don't have GPUs." And I like, man, not every model requires GPU. 99% of the model, you can just train it on your MacBook. Okay. And you'll see that as we go ahead. Okay. The gradient descent is very efficient and greedy algorithm, and it's actually pretty fast. Okay. So everybody okay with this? Now you can code it. Yeah. Tell me, can you code it?
Yes.
Okay.
I mean, I don't know if it was similar, but the line detail which I had coded, right? It sort of did the same thing, right? I mean, rather than calculating this, it calculated the mean of all the errors and tried to match it rather than change the slope.
Yes. That's the beauty of doing it by yourself, the first principle. When you do things first principle, you can connect the dots very quickly. That's why I'm a big fan of doing it like a kid, using the first principle, rather than reading someone's manual, rather than following the instruction or a video. I just try to do things first principles. If I know that, okay, it's not a poison and it's not going to blast, I do things with first principle. Okay, it's okay to make mistakes because what we are looking for is the people who can think in first principle. Okay, a big trouble that I see, honestly, I was attending this talk and this guy just said, "Oh, why do you invent? Why do you need to invent? Because somebody has already done the same thing somewhere." And I was like, wow, right? And this is a Google marketing guy. Why do you need to invent? Somebody has already done it somewhere. Why don't you just go and search about it? And this is exactly the I feel that that's the advice that engineers should never follow. Okay, at least from my perspective, I'm not looking for somebody who just copy paste a solution from somewhere. I'm looking for people in my class who can debug it, who can build tools, who can build systems, okay, who can build things, and only those people who can invent, who think in terms of first principle. Okay. And yeah, that is the most important thing to do. I want everybody to try doing these things in the first principle. Just try. Just think of it that whatever you're going to do is not going to blast my computer. The computer is not going to say no to me. Okay. At most, there'll be error. I'll debug it. Okay. Just give it a shot. Just give it a shot. It's completely okay. It's completely okay. For example, I'll show you. Okay. Okay. So I just thought that, okay, let me see if I can optimize the gradient descent. Okay. So I came up with my strategy and everything. All right. And I wrote the entire gradient descent method, and it did not work. Okay. But I do not regret it because it taught me so many things. Okay. And yeah, the easiest way to do in life is never try, never fail. Okay. But I think that's something that I would not want in my class. I want everybody just give it a try. Fail, it's okay. No shame in it. Just like a kid, just keep experimenting, try more and more things. There's nothing wrong. Okay. A bad habit that we develop as part of, so-called gaining the experience and growing up. One bad habit that we develop is that we always want to just read first, memorize somebody else's solution and then, use it rather than going first principle. Okay, so I would want everybody to do the first principle things, and trust me, it's going to be fun. Okay, it's going to be fun, and you will cherish that. Okay, all right, moving on. Having said that, if you truly understood what we did in the class, the gradient descent algorithm, if you truly understood the steps, you should be able to code it. You should be able to write the code of the same thing. Okay, so who can help me write the code of this? Anyone? Anyone wants to give it a shot? Do you think we can write it in like next half an hour? No? Okay. All right. So first of all, let's define a function. Let me just put it in another notebook. Okay. All right. I'm just going to put it in another notebook. That notebook, I think we should put it in our usual folder, correct? This one, right? I'll just put it in here. Okay. Okay. All right. See, my definition of learning music is you should be able to create your own music. My definition of learning machine learning is you should be able to write your own algorithm. You should be able to come up with new algorithm. Okay. I mean, that's how I look at it. Okay. And yeah. So that's the most important part. Okay. This class is not about you basically copy paste the algorithm from library and then say, okay, if that algorithm is not working, it's the problem with the algorithm, and it's not my problem. That's not why we are in this class. Okay, we are in this class because if something doesn't work, you should be able to just take it up and break it apart and then look at it, what's going on. Okay. And trust me, that happens very frequently. Like in the recent project that I'm working on, we realized that we want a very different loss function. So we had to come up with our own loss function, though we kept everything else as such. Okay. All right, let's start. Okay, so where do we start? What we want to do is we want to code this formula. Okay, m dash equals to m minus eta times what? dE by dm. Okay, now how to do this? All right, the challenge here is this: how do you calculate rate of change of error with respect to m? Okay, let's define some points. Okay, let's define points. Okay, data points. Let's say for 1, the value is 2.1. Let's just how to cleverly come up with the data. Okay, how to cleverly come up with the data. I'll just say for I in range, for x in range 1 to 10. Okay, and then I will print x comma. Okay, or I'll just put it in this array. Okay, my data equals, I'm just synthesizing data. All right, I'm just going to synthesize data. Data dot append And there we go. Everyone, even if you have not attended any of the classes, please feel free to ask what's going on. Don't assume that it's your mistake that you did not attend previous classes. This class is fairly independent from what we've studied so far. Okay, so right now we are synthesizing data so that we can fit our data into something, right? Now, question is, what should be we should do, like, instead of just randomly generating data, we should have some intelligent way of generating data. So we are saying that, okay, our y is going to be something like 10 times x, okay, plus 10. Okay, and here I'm just adding, say, random dot random, just tiny bit of randomness. Okay, and there we go. I'm just adding some randomness. Okay, and all right, I'll just make it a little tiny. Okay, it should not become very awkward. Okay, import matplotlib.pyplot as plt. I just want to see if I can plot this data. Will it plot it? Yeah, this, oh, it basically plotted 2 lines separately. Okay, how do I pick the x from that? What would be a good way of getting the x? Okay, data dot, oh man. Okay, what if I just for a moment, I'll just take out this I think what it has done is it has put this separately. Okay, so I will just extract right, using this map function. I can extract. Okay, map function finished. What does it mean? Anybody? Okay, I'll just try to see what's there inside it. Yeah, so it did good job. Okay, all right, this is my y, or should I just put it in x and y? Okay, I'll just put it in x.
You need x and y, 2 arrays to plot, right?
Okay, I'll just put it in this. All right, I would keep x dot append x and y dot append y. You were saying? I missed that part.
No, I think you need x and y to plot that array.
Yeah, that's what I'm realizing. Yeah, now it makes sense. Okay, so this looks like a little easier. So I'll just try to make it this. Okay, and what should I do? Yeah. Okay, I'll just see if this makes any sense. Yeah, this looks okay. Let's see. All right. Now it looks better, right? These points. Make sense, everyone? This is
Yep.
the data we have generated, okay? This is the data we have generated. I hope everybody is clear about what I've done here, right? Okay, good. So we just generated some random data. Me and you know that the equation of line is 10x plus 10, but we are not going to tell the algorithm this. Okay. Okay. Now, first thing is, given the value of M and C, okay, how much is the loss? Can somebody tell? This is my X and Y value. Okay. So given, let's say we are making a random guess of line, and we want to compute the overall loss. Okay. Well, let's call it squared loss. Okay. So what we're going to do for this M and C, okay, predicted is going to be equal to X times M plus C, correct? And we are going to do this for all values in capital X, right? And then I will do the enumerate, okay? Is everybody with me so far? Okay. And right, actual is how much? Actual is, this is predicted Y, this is actual Y. How much is actual Y? Capital Y. Okay. Now error is how much? Actual Y minus or predicted Y minus actual, doesn't matter. Okay. And we are carrying total squared error equals 0. And then we are saying error times error. So this is my squared error. Okay. Is everybody okay so far? This is my squared error. All right. Now, we are going to compute the rate of change. Okay. We're going to say, we are going to define a function called, this is the function. And okay. Now, one important thing I want to do is, I want to pass these values like an like an array. Okay, like an array. Okay, and I want to say M comma C equals weights. Right? Is that okay? So I'm passing it like an array and then assigning it to this. Okay. I think this is how you do it, right? Let's see. M comma C equals 2 comma 3. Right? So you can see M and C. Okay. Now if I do this, will it work? Yeah, it's working fine. So doesn't matter. We can just keep it like this. Everybody okay so far? Any doubts on this? We wrote two pieces of code. First piece of code generates data. Everyone? If anybody has doubt, please raise your hand. Ask the question now.
This error calculation, we fixed it as the squared error, right? This loss function means whatever is the error criteria that we are taking.
Yes.
Okay.
Correct.
That we are fixing it with the earlier experience that we are fixing it, that it should
Yes.
be.
Yes. Yes. Okay. Now we are going to do this, that we are going to say that compute the value of compute the squared loss, compute the rate of change. How do you compute the rate of change? Everyone? Okay. Let's compute the rate of change. Okay. Let's see if it works. Who can help me? Differentiation of a function f at value x. Okay. Imagine, I'm just taking a bit of digression. Imagine your function f is, let's say, this. Okay. It takes x, returns x squared. How would you compute the rate of change of x with respect to x? Can anybody help me? Yes, the way we have calculated in Excel sheet, same way. How do you compute the differentiation of a function? The first principle, what does it mean by the differentiation? Okay, rate of change. We want to compute the rate of change of f with the rate of change of output of f with respect to x. Okay, how do you do that? Everyone? All we want to do is increase x little bit and observe the change in outcome. Correct? So let's say the previous outcome was, let's say, E. Okay? Everyone okay? And then we increased x a little bit. Let's say x was increased by delta. Let's say this delta is very tiny, right? Delta is really, really tiny. Okay, this much. So we increased x by little delta, and then how much is the rate of change of output? It is E1 minus E divided by delta. That's it. Is that it? Let's take a look. Okay, so let's say this is my squared function. Okay, and what's the differentiation of this squared function at x equal to 10? 20. You see that? At 12, 24. Are you guys okay? What I did here, this magic? No? All I did was I increased x, the input. If you, the way you should visualize it is this, okay? The f, okay?
What? Sorry, what is f? I'm not very yet familiar with Python, but what is this equal to f of x? What is f?
So in Python, you can pass a function as argument.
Okay.
So we handed over the function f as argument, and then we called that function.
Okay.
So we are calling that function here. You see that?
Oh, the square. Okay. Okay. Got
okay.
Diff of square. Okay.
Yes. This square, we passed it as is. Got it? Okay. So the way you should see is that to this function, we are giving f. F is some function which takes some input and gives output. Okay. So what we are doing is we observed how much was y at x. Then we increased x by a little bit. Then observed how much was new value of y. And then we reported return on investment saying y dash minus y divided by delta. Delta is how much we increased.
Okay.
Everybody?
Yes, got it. Thanks.
Okay. So this is probably the simplest definition of differentiation or derivative, or is there any other term for differentiation? It's essentially the rate of change of output with respect to input. Is everybody okay with this definition?
Yes.
Sandeep, I had a question. In differentiation, would it be not like increased by the original rather than delta? Like difference between the two data points and divided by the original one.
1 second, there is an echo.
So the return statement, right? It should be with respect to E,
So
if you're looking at the rate.
This one?
Yes.
No, it's basically what we did was, this is my input variable, okay? At x equal to some value, we want to calculate the rate of change of error, rate of change of output, right? So you can think of it this way. Okay, the x is this, okay? And x1 is equal to x plus delta, okay? And then we feed x1, we get this, okay? And we are returning rate of change of output by rate of change of input. Got it? Rate of change of output. If you want to change E to Y, that'll be easier, even further easier to visualize. Okay. It's the variable names that actually, I mean, my laziness of typing big variable names would cause a lot of confusion to you. Okay.
Okay, yeah. Now it's
good?
Yes.
Okay. So if you notice that x1 minus x is essentially delta. So this calculation is unnecessarily extra. That's why I just kept, I did not use this. I just said, okay, just use delta. That's all. Got it?
Yeah, thank you.
Okay, so everybody on the same page? So the way you should visualize is that there is a machinery called F. We are feeding it X. We are getting Y from it. So we first fed some value of X, let's say 10. And this machinery is a square. And then it gave us 100. Then we fed it 10.0000001. Then it gave us how much? It gave us 100.00002. Like that. And then we subtracted this from this, and we reported the ratio of the change. Okay, that turns out to be this. Yeah. So you will notice that the derivative of square at x equal to 10 is 20, x equal to 12 is 24. Yeah.
Here is the equation is square, right? Like y equal to mx plus c, we were earlier example. So now it is like y equal to x square, right? Is this? Or I'm
no, this is separate. This is separate. This is a general differentiation formula.
no, this is that square of x. You are using this. So any function we can use, right?
Yes.
So you want to say like y equal to mx plus c, whatever we can. Okay.
Hey Sandeep, in that diff function, we haven't defined x1. So where is x1 coming from in the diff function?
Oh yeah, that's wrong. So it was x plus delta.
Okay.
Okay, we increased x a little bit and observe how much did y change on that increase.
Okay, and this function will be used in calculating whether we have to like in that formula, right?
Yes.
Okay.
Yes. Okay. Is everybody okay with this so far? Perfect. This differentiation calculation is good so far, right?
Yes, yes.
All right, perfect, perfect. Now, the problem is that where we are going to call this f, this function is taking an array of values instead of a single variable. This one was good when we were doing the differentiation of a function which were only taking one variable, right? We want to pass on two variables now, okay? So what we're going to do is we're going to define a little modified version of this one, okay? We are going to say f, and we are saying weights, okay? And the index on which of the weight do you want to differentiate this function at, okay? So we basically, and let's call instead of f, we'll call it loss function, okay? So we are saying first call the loss function on the weights as is, okay? And then increase that particular weight, okay? All right. I'll have to write idx, okay? I'm using a wrong method, but you understand. So I'll just save its value somewhere so that I don't modify it, okay? And okay, I'm saying increase the ith weight by this delta, okay? And then again calculate the weight on this value. That's it. And you return the value of right, y1 minus y divided by delta. Happy? Is everybody okay with this? So first of all, are you okay with this here? Are you okay with this differentiation definition? Remember, like, what is differentiation? Differentiation is, right, if you have a function which takes an input and it gives an output, the y, right? Differentiation is nothing but delta y by delta x, okay? Where delta x is tiny, tiny, when the delta x is really tiny, okay? So as you, what is the rate of change of output with respect to rate of change of input? Or you can say, how much did output increase when we increased input? Okay, that is our rate of increase. That's what we have calculated. We took a tiny value and we increased x with that, and that's about it. Yeah. Everyone, please stop me if there is any confusion right now.
So how did you choose the function of square, like depth square x? On what basis did you choose that?
Here?
Yeah.
The square loss.
No, the bottom one, depth
This one?
square x. Yeah, this one.
This one just for experimentation. Okay, you can define, let's say, cube, and just to test out what I'm doing here is making sense or not. You can also define, let's say, cube. Okay, I'm just saying cube. Okay, let's say cube, and the value of, let's say, cube is return x times x times x, and check if the cube is making sense. Okay, so can somebody tell me from your calculation how much this value should be?
36.
Are you sure? Not 36, you forgot. 36 times 1, 12.
432.
Right? Okay, let's see. You can see it's not that bad, right?
Sandeep, what is this loss f? I didn't get that. I'm sorry.
We will
Loss.
come back to that. We'll come back to that.
Oh.
Okay. Here, slight digression. Okay. Here, coding like differentiation. Okay, I'm just trying to, right? I just want everybody to be on the same page with respect to differentiation. Okay, differentiation, let's think, but when somebody says differentiation or derivative or in calculus, right? It doesn't mean that we have to differentiate two value, like find the difference between two things. Okay, it means we want to find out the rate of change of output with respect to some variable. Okay, as simple as that, right? Rate of, like when we are going from one place to another, rate of change of position with respect to time is called velocity. Rate of change of velocity with respect to time is called acceleration, like that. Okay, so essentially we are trying to calculate that rate of change. Okay, so we define a function f which takes another function as argument, and it takes some value at which we have to calculate. And this is a numeric differentiation. We are trying to calculate the value at a certain value. Okay, we are saying when x is this, how much will be the rate of change? Okay, got it? Right?
Okay.
Yep. It is like, let's say we draw a curve. Okay, let's say there is x, there is y, and let's say there is this curve. Okay, meaning this curve is denoting how is the output changing with respect to input. This curve is denoting that how much will be the output when x is given. Okay, so let's say we are given x equal to 10. So let's say y is this much at x equal to 10. When we increased x a little bit, our y increased to this. Okay, so if you see, this perpendicular of this triangle is new y minus old y. The base of this triangle is old x and new x, correct? So if you make this triangle a little bit, zoom it, this is how it look like. Delta x, delta y. Okay, so we are trying to calculate delta y by delta x. Okay, that's usually denoted by the slope of this line. Okay, so that's another way of looking at differentiation. So if you plot the output of a function with respect to input, you basically get some sort of a curve. The slope of that, right? The slope of the line that you draw is called the differentiation. Like here, the slope is going to be a little heavy, right? And so on. Is everybody okay so far? No?
Yes, Sandeep.
Yes.
All right. Please feel free to ask if you have any doubts. Any doubts? Yeah. Okay. Those who are thinking that they did not study the calculus, therefore they are not able to understand, please note that even those who studied calculus and did their masters never coded a differentiation formula. They hardly ever did numeric differentiation. And it's a very interesting phenomena that I was interviewing this guy from one of the top research companies. I asked him about how does gradient descent work. So he says that we calculate this and that. And I asked him, like, what if our square loss is, like, instead of square loss, we are having our own logic, like if else condition is there, then how would you calculate the gradient? And then he said, oh, that I don't know. And he actually thought that we are going to use the standard algebra to do the differentiation. He did not realize that we do the numeric differentiation the way we are doing here. Okay. And it's a very interesting phenomena that even the PhDs and masters in the domain in machine learning, they have not really understood how we do the gradient. Okay, so if you're not able to grasp it, it is basically not because you did not study things. It's just because these are new things. So just ask. If you have any doubt at this point of time, please ask. Okay. For you, it might look right now that it's very easy and flowy, like simple. It's because I'm typing quickly and smoothly without any mistakes. That's why it looks like pretty simple. But when you code it by yourself, you'll realize it. So I want everybody to question it and ask me at every point of time. Okay. All right. So is everybody okay? No? Yes?
Sandeep, one question on the value of delta, the more less will keep, would it be more accurate?
That's correct.
Okay.
Yeah. The smaller the value, the better would be the thing. Because the whole principle is that just because of increasing X, it should not impact your outcome. So that's why you want to basically just increase X little bit, tiny little bit, and then observe the change.
Sandeep, I have one question. Like we do binary search, right? So now we can search for the slope we want to find, right? So lower, we are trying to draw a line in the lower level, and next time we are going higher. So we can take the mid of this.
Okay, that's what I thought that I'll do. Okay, it did not work. Okay. Anyway, you should take a look at the one that I showed. Okay. So I actually did the same thing. Okay. Yeah. All right. So, but those strategies are good, but you should give them a try. Okay. If you're getting an idea, just code it up. Okay. Just code it up and test it out. Okay.
But why didn't it work?
You should try it out and you will get that reason there. Okay. Okay. One is like if you think about binary search, right? The thing is that if you keep increasing M, the error will not keep on decreasing, correct? You don't know. And then because the optimal lies in somewhere middle. Binary search is good when you know that increasing will increase indefinitely. Okay. And because the data is ordered and you know that the loss is going to be like that. So you can keep on doubling fearlessly. Here, you go up, down, and that's what is the binary. So you draw the line below, then up, above, then below, then above. Like that's what it does. Okay. Because the minima lies somewhere like this. If you draw, let's say, error versus slope, right? At very small slope, the error could be high, and at very high, the error could be also high. So it could be somewhere like this, correct? So if you draw the error, like if you pay attention here, right? For very small slope, the error is high. For very high slope, the error is high. Correct? So there is no, unlike a binary search, here the magic lies somewhere in between, not on extremes. Okay. In case of binary search, either the data is decreasing order or increasing order. It's not like this. Got it?
Yes. Here actually we don't know the lower and upper limit actually, I think.
Yes. Yes. And we don't know. We basically, even if we knew the lower and upper limit, we don't know where in the midway it is. Got it? Yeah. Perfect. Very good questions. Very good questions. Keep these questions coming. It just tells me that you are on the same page as myself. Okay. So I just showed you how to differentiate a function which takes only one argument. Okay. How do you differentiate a function which takes multiple arguments, like this one is taking multiple arguments? Okay. Please note that even for the multiple arguments function, we only increase one variable at a time. Okay. This is called partial derivative. We increase only one variable at a time. Okay. So here what we are saying is, find the rate of change of this function, the output of this function, given these input values with respect to this value. Okay, this particular index here we want to do. Okay, here the only trouble we are making is we are kind of destroying and changing the weights. We were not supposed to do this. Okay, so what you can do is we can make the copy of the weights. Okay, copy, right? COPY. And okay, and we will basically just keep it like this. That's it. So we just made a copy of weights internally, modified that, and then used it. Oh, everyone okay so far? Am I making sense? Now for this, let's just test out the, right? We can compute the rate of change of, right? Okay, we can say diff. And what was the name of the function? Squared loss. And let's say the weights we are passing is, let's say 10, 10, just to, okay. And, okay, what does it say? Squared loss, it has a missing positional argument. Okay, squared loss. Okay, let me go up. And that's it. Okay, it says error is not defined. Where did we make that mistake? Error, error. Okay, there we are. Now it says weight is not defined. Okay, weight is not defined. Where did we make this?
Line number
No,
5 in the last.
Line
it
number
should be
5.
weight.
And the last one.
Weights.
Yeah,
Oh,
it should be weights.
now it says the operator not supported on none type. Line number this. Okay, it did not, our function did not return this total error.
X
Okay.
and Y first here.
What?
X and Y. In line number 4, we are using X.
Here, right?
No, in the same square loss method.
This one.
Yeah,
Oh,
line
yeah, yeah. Yeah. Okay. Ideally, we should actually pass, okay, X and Y. You see, capital, we are using these global variables, these X and Y that we defined earlier. That's our data.
Okay.
Got it? Ideally, we should pass that here. Okay. But right now, I'm just using that as a global data. Okay. Now, moving ahead. Yes. So you can see at this value, the rate of change of squared loss because of the first variable is this much. Second variable is this much. Okay. And all right, let's just see. Okay. Right. I would say 1 here. Okay. All right. You can see here, this is negative, right? Rate of change is negative. Okay. What does it mean? That the the loss is going to the error will basically drop if you increase increase slope. If you increase this, then the error is going to drop. That's what this negative value means. So we are good so far. Is everybody okay with this function, what we did?
The first variable is the slope, right? And the second one is C, right? So which means that if we reduce the slope, the diff is giving negative value, which is rate of error, which means that we are getting success. Okay.
Yeah. I'm just wondering, did I make mistake? Okay. I've done some randomization here. Okay. Should I try making it a little bit more, little less random? This is just too nice. Mm-hmm. Doesn't it look really strange?
What's the problem with this data set, Sandeep? Why are we changing it?
It just looks too nice. Okay. I want it to be a little more random. This is way better. It just looks too nice. That's the only problem I'm having. Yeah, this is okay. All right. Okay, so everybody okay? We calculated the loss function. We also computed the differentiation of it. And we have this function which takes loss function. Also, it takes the values on like the weights, the slope and intercept. And there we have it. Okay.
So
Now,
Sandeep, we will have to do it for each value, right? We are just doing it for one in each line. The index will have to go from 0 to the entire data set, right?
Yes. And not entire data set. We are doing it for all, right? If you see, we are going over entire data set here. So this is how we are computing the loss. We are given these weights, okay? For every value of X, we are predicting value of Y, okay? Using these weights. And then we are calculating the error. You see that?
Then what is the third parameter signifies? Sorry. In the last function?
Third parameter. Okay.
Index.
Yeah, whether you want to differentiate this function with respect to slope or intercept.
Oh, okay. M or C.
M or C. Okay. 0 means M. Okay. We are differentiating it with respect to 0. And the M, you can see, I am increasing only that particular weight. You can see, I'm only increasing that particular weight. Okay. That's all. Got it? So we increase the slope or intercept depending upon what is our index value. Okay. If index is 0, we are tweaking M. If index is 1, we are tweaking C.
We could have written two different functions as well, right? For M and C.
Yes, but I'm super lazy.
Okay.
No, I mean you don't even need two different functions, right? I mean, rather than sending weights, you could have yeah, I mean no,
Okay.
I mean in the same function, right? You could have checked for
So
M and C both.
basically, this is my partial derivative function. It takes a loss function. it takes a function which takes multiple arguments, and it also takes the, like, which variable do you want to differentiate with respect to? Okay, so it calls that function first with those all the weights, and then it increases one of the weights depending upon index, and then again computes the loss, and then computes the rate of change.
So if you have an equation, if you have a
100 variables,
an order equation,
yeah, if you have 100 weights, you just keep on changing the index.
Sandeep, one question here. Weight, why we have 100? We weight always the M and C, na? They always the 2.
No, there could be 100, right? Let's say you have a 3-dimensional equation, right? Like you have 3D, correct? You have, right, x1, x2, and y, right? So what will you predict? Your model will look like this. Y is something multiplied by x1, something multiplied with x2, plus some constant. So you got 3 variables now. Okay, so you have to find those 3 values. So you got a plane to fit in 3D.
But when you go to the upper this loss of method, then weight convert to the M and C. Then weight is the 3 variable. Then that is not fulfill the our scenario. Is the loss of method weight equal to M and C? That's the tuple variable, right?
Yes.
If we put the 3 variable inside, then
you are right.
that is not.
So you have to basically change this.
Yeah.
Instead of M and C, what you have to do, you have to multiply one array of numbers with
based on
another.
the
Correct? So that generalization, I completely agree with you. Okay. Right now we are assuming that it's only having 2 variables.
2 variables, right? Yeah.
Okay. But we can simply change that. Instead of assigning it to variables here,
but
we can also...
one question, and again, weight have the multiple, like M have the multiple value, then how to this calculation then? Prediction of the X into M plus C. Then for every M we calculate the new prediction for the X value.
Yeah, we'll call this square loss for separately.
Separately.
Each M and C, each M and C. Okay.
Okay.
All right. Everybody good so far? Now, let's define our train function. Okay. What we're going to do is we are going to guess the value of M and C. Okay. Just random. Okay. We just started with random. Okay. Now, let's see. This is my M and C. Okay. Now, I can also call them my weights. Okay. I will just call them WEIGHT as weights and put them in square brackets. Happy? Initially, we drew a random line. Okay. With the random slope and a random constant. Cool. Now, what we're going to do is we are going to, let's say, run this next step 100 times. Okay. I'm just going to say for epoch in range 100. We're going to run all the calculation below this point 100 times. Okay. And what we're going to do is we are going to take these weights, whatever we have chosen randomly. Okay. Calculate the rate of change of DEDM. Okay, rate of change of error by M. Okay. So how do you do that? You basically call diff squared loss, and I pass weights. Okay. And I also pass the variable. Okay. Similarly, I calculate the value of dE by dC, the rate of change of error with respect to intercept, correct? And then I say new error, okay? Okay, new slope is equal to old slope minus eta. Eta let's just keep it here. Eta equals 0.001. Okay, we will experiment on this. All right, and okay, what do we do now? Okay, also what we can also do is we can calculate the squared loss right now, right? Print current error or current loss. Same thing, I'm just using that. Okay, so we are doing that. And we can also print our iteration, right? Okay, at this iteration, this was the loss. Very simple. Similarly, C1 equals and M comma C equals M1 C1. Good. All right. Yes. All right. So initially,
Sandeep, sorry. Shouldn't the eta should be same as what we have taken in the def function?
come again.
So in the def function, we have taken a step, right?
Yes. Yes.
So shouldn't that be same as what we have defined in ETA?
No. It's a different thing. This eta means for the rate of change, how much do you want to tweak your variable? Okay, that one is the limits one. That's the definition, like minimum possible value. Got it? Okay, that one is that.
This is the rate. This is the rate of.
You want to, yeah. Next step, how big a size do you want to take? Like how big a step do you want to take? Got it?
So basically, in def, we are just doing minimal change and seeing if we are getting positive or negative. If
Yes.
based on that, we are taking the step. So we are doing the same calculation twice, sort of, right? We'll be doing the diff.
This one, right?
Yeah.
Yeah, kind of, yes.
Okay.
And one more, what is the initial M and C for line number 7 or 8?
This one here.
Yeah, M and C value. What is the first iteration?
Oh, you are right. So good question. So what we're going to do is we are going to just say good question. And we are not using the value of these things properly. Okay, what we're going to do is M equals random.random and C equals random.random. Okay, and then I'm again going to put them and we'll like this. Weight equals. I think this is better way of dealing with it. I'm also going to print these weights. Okay, so let's take a look. Initially, the error rate was very high. You see that? Initially, the error was 35,197. When M was this, C was this. Okay, then we calculated the squared loss we got new M this, new C this, and the error was this much. You can see the next error is 1200, then it reaches 188, and then it has reached 108. Okay. So
But
should I run this loop for a little bit more time?
yeah,
But if we increase the ETA here,
yeah,
then we will have, means in 1000 iterations we will have much better output, right?
let's see.
We could have.
Let's see. Okay. I'll just show you something. Let's just experiment on this. Okay. So let's just start from the beginning. So I resetted the value of M and C. Okay. Now this time we are going to have this value as 500. Okay. Now take a look at this. Okay. It's jumping, you see? Suddenly the loss has become really big. Got it. What happened? What happened was this was my data, and we came up with this line here. And then instead of taking a small step like this, what we did, we took a really big step. We took a really big step from here to here. And then this was further more. So we took a further step like this, then further bigger, further bigger, further bigger, right? And it has gone mad. You see, 10 to
but
the power.
Sandeep,
No,
but
but if we
after
make it one, if we make it one, then
Yes,
so
let's
basically
test
we are
it.
then eliminating
Yeah, let's
ETA
test
from
it out.
learning rate from the equation.
Let's test it out. Still, it is again. Let me reset these values, and then one is still not good. You see, it's still bouncing. Okay, let's go with 0.1. Okay, let's see. 0.1 is still bouncing. It's increasing a lot. 0.01. Let's test it out. 0.01 is still bouncing. Why? And let's just do this. Now, 0.001 is okay. All right. So got it. So what I'm trying to show is that maybe it is little smaller, but that's okay. If you, let's say you have very small value, it will converge slowly. You can see it's converging slowly, but it's converging. See that? Okay. And it won't basically, you can see I'm running again. So I can run it like 5-10 more times. Let's say go for 1000 iteration. Okay. So you can see it is going slower, but after a while it is settling down. You see that? So
that means Sandeep, eta value depend on the number of iteration. If we have the lower value, then more iteration we need for the final result.
no, not really. That's what I was saying. All you have to ensure is eta value should be such that it doesn't jump back and forth. Okay, that's the only problem with eta. Rather than converging, it is diverging. Okay, so keep the eta value such that it doesn't diverge. Or let me put it the other way. When you observe that it's just increasing, error is increasing, bring down the eta value. Okay, just bring down by 1 decimal point.
One major result I observed that if the eta is 500, after 2 iteration, the MNC value is constant, not changing for the any iteration.
Which one? 500.
Yeah, eta is 500.
Yeah, it basically it has gone to infinite.
Then not changing to the anything for the further process.
Yeah. It basically has reached its upper limit and no longer just going anywhere. Okay. So yeah, it's just gone crazy. All right. So yes, trust the gradient. Yeah, the eta, basically the thumb rule is if the whole process is going super slow, try increasing eta. If it starts diverging rather than reducing, then decrease the eta. Okay. Everybody on the same page?
If the eta value is very low, Does it have a relation with overfitting?
Eta value is very low. Eta value is very low. Let's just test it out. Okay. I'm starting again from the random. Okay. The only problem here is that with eta value being so low, that it's just moving it slowly, right? 33,000 was the error, then it brought it to 30,000, then it brought it to 10,000, then it brought it to, you can see, it is bringing it down, but it is bringing, you see that? It is bringing, okay? So there are quite a few strategies. We call them learning rate scheduling. Okay, take a look at learning rate scheduling. Okay, what people usually do is initially they keep the eta to be bigger, then they reduce the eta later so that it basically doesn't really jump back and forth. Okay, so learning rate scheduling comes from the same strategy that when you are just almost reached there, don't jump too much, just do it nearby. So people keep on reducing the eta as they reach to the final place. Okay. All right, so this is it. Now your machine learning course is over and you're all happy. All right.
Sandeep, my question was that if we keep it too low, right? Or if we reach a too low a value, will it reach to overfitting of the model?
Not really. Overfitting depends upon few more situations. Okay. Overfitting is a function of memorization, right? So sometimes what happens is your model starts to perform, starts to memorize it. Okay. The more number of iterations you go through, right? After a while, what happens is, like here, right now, we are only printing the loss on the data on which we are training, correct? You usually, what you also do is you compute the loss on the data which this model has not seen, okay? So you keep one set of data that this model is not trained on. That's your testing data. And then you observe, is the loss going down for that data set also, the unseen data set? If that is also going down, that means we are going well. The moment, after a while, what will happen is when it keeps on, you keep on beating this model again and again. So it will start to memorize the data points. Okay. And then at that point, when it starts to memorize the data points as is, its performance on unseen data will drop. So the loss function, instead of decreasing, it will start increasing on the unseen data. Okay, it's like a kid who has memorized and mugged up everything from the textbook over and over, and then after a point of time, the kid will not be able to perform in the exam because kid has memorized the notebook, a textbook, right? That's basically the point. So epoch has direct relationship with overfitting. Eta does not have. Okay.
Okay.
We'll talk about that more later. All right. Is everybody okay? So we coded the gradient descent. I would want everyone to code in your own style. Whatever you studied in the class, that's all good. But I want you guys to just start with a blank notebook, the way I started today, and then start coding it. Okay?
Sandeep, one question here. Like
yes.
For via this gradient descent, we calculate the MNC. But anyway, can we figure out the y value is the max value and the minimum value? Like any point x, we figure out the y reach to this maximum point and y reach to this minimum point. So
okay.
What is the?
It's very difficult to figure that out. Okay. If we figure that out, then everything would have been easier. All right. Perfect. I think
Sandeep, one last thing.
So what is your answer? I missed that. Sorry.
Gaurav,
What is
I'm
your
saying that it is not really. You are saying that value of M and C, if we can figure out the max and min values of those, right?
Yeah.
Yeah, I think our agenda is to figure out the minimum loss, correct? Error, and we focus on that. Yes, getting the, like, what do you want to do with that if you want to find out the min and max value of M and C?
Like I see this chart of the being the share market. You see the graphs of the share market. He predict the value of the buy, but same point he also defined that this is the maximum value we reach that and the minimum value we reach that. Like the buy curve, we can denote the U curve. So how to identify that is my question. What is the any way or any other algorithm we can predict that this thing? Because of the future prediction of the y value, same time we predict the
No, so
what
what
is
you
the
usually do is you design, let's say, your model, right? You design two models. One is predicting y min, other is predicting y max. Okay. So you have now two models. Both these models are predicting these range, and then you can calculate the value within that range. Got it?
The other way, I mean, to answer this point, right? The other way, what we can do is once you get MNC, you can calculate Y, and then you can backtrace and see what is the deviation of each of the data point with the slope which you have derived, and that deviation can give you the range of your new calculated Y.
Yeah.
Does that make sense, Sandeep?
Right. I think, yeah, I'm still not very clear, but so he's trying
just
to figure out. So I think his question is with respect to the stock market specifically.
Yeah. So for the same reason, right? For the same thing, with MNC which you calculated now, this is not 100% fitting for the data points which we have. Correct? Right? So with this MNC also, when we recalculate X and Y for the given data set, we will see deviation.
Right.
Which means that we can calculate that deviation, and then for the every new value which we calculate, we can say that can be the deviation for that value, so we can get the range of it, isn't it?
I think I got what you're trying to say. So Gaurav, what he's trying to say is that you can calculate a model's performance or error range. That model on an average is giving this much error in the prediction. Correct? That's what you're saying. And then you can say that on an average, my model is giving this much error plus minus this. So whatever I'm predicting, put plus minus this value. Okay. But I think your question was very much specific to the high and low value in the stock market. Correct?
Not a stock market. I see some chart where some model predict this point of that is the mean value. Yeah, band something, the upper band and lower band. How to calculate that for the specific point?
So I think both the strategies are okay. One is a static value based on the current error rate that is going on. One is that, and like compute the average of based on the test data. You compute the average range, and other is just design your model in a way that you are like predicting y low, y high, and you can use that. Those have two separate models for that. Okay. That could be another value. All right.
No, Sandeep, one last thing. So to code the logic to code this gradient descent, right, would almost be similar to what you have done, or would there be completely different
No, I
logics or
think
strategies?
no. I'm saying that just reproduce it, whatever we.
That is fine. Okay.
Yeah, it's up to you, and right, and I would be more than happy if you take a digression and make in your own style. Completely okay. Okay, but I want everybody to code their own gradient descent. Okay. And if you can come up with better strategy than or any other strategy than gradient descent, I welcome that also. But I want you guys, everybody, to code your own gradient descent. All right.
The way we calculate the loss is going to be same, right? I mean, we can't sort of diverse from that, right? The loss calculating function, the square loss, that's going to be the same. I mean, there are no other
Yeah.
way of calculating loss.
I mean, there are ways to calculate loss. You can try the Huber loss even in this case.
Yeah,
It's
and instead of the mean square deviation, we can have the absolute function, right, as well.
Yeah. And notice that this one is giving 9.7 as my coefficient for M and 11.6. And actually was how much? Actually, we started with our data. You can see here, where was that? 10x plus 10. So because of the randomness, it has been a little different. Okay. So yes, that's pretty much.
Sandeep, one last question. So we talked about gradient descent. Earlier we talked about linear regression. So
Yeah.
I find that like both to be coinciding. Like we can do the linear regression with the help of gradient descent.
Yeah. So linear regression, okay, is basically here can be done. What is linear regression? We are trying to fit a straight line in the data points, okay, and the algorithm, or we call that optimizer. We call that optimizer is gradient descent. There are other optimizers as well. There are other algorithms such as what is it? Least normal equation. Let's just call it normal equation. We'll talk about normal equation. Okay. The classification, we call that logistic regression. Okay. Right now we are predicting a value. Sometimes you want to predict a class, right? Yes or no. Okay. In that case, also, we use the optimizer as a gradient descent. Okay. The gradient descent with a different loss function. Okay. We'll talk about those during the class. Okay. So in case of, let's say, a neural network, okay, we will again use the gradient descent. In this also, the optimizer is the gradient descent. Okay. And we'll basically do the neural network. We in case of this, we'll have like lots and lots of M and M1, M2, M3, M4, like there are hundreds of them, and we'll use the optimizer as gradient descent. There are other variations of gradient descent that we'll talk during the course, and there are other alternatives to it. Okay. In case of here, we call that, this algorithm as back propagation. Okay. Still, it's essentially gradient descent. We start tweaking the weights from right-hand side of the neural network to the left. We'll talk about those during the course. But the most important thing to keep in mind that here we are solving a problem of regression using a linear model, meaning we are fitting a straight line through it, and the strategy to find the weights is done by gradient descent. All right. I hope the keywords are not confusing.
Yeah, got it.
Okay. Regression means predicting a value. Classification means predicting yes or no, or predicting a class of things, A or B or C. Okay. We'll talk about those later. Right now, we just focused on regression, and that's all. All right. Perfect, everybody. Okay. Because it's easier to do the regression for beginners, easier to code the gradient descent for regression. We will talk about that for the classification soon. The loss function will be different, basically. Okay. But the algorithm is going to be the same. All right. So I want everybody to code it up and right by tomorrow. All right, during tomorrow's class. Have a good day. Bye-bye. And in case you need help, you just search for, gradient. I've done it. Yeah. Okay. Yeah, this one. Okay. If you need help, you can basically just, take a look at, right? This. Okay. All right. I'm just committing it before we, what's the date today? Date today is 17 August.
August 17.
Okay. Now, let me just commit it. All right. Done? All right. Now you can go ahead and give it a shot. Everyone, have a good day. Thank you.
Okay. Thanks.
See you tomorrow.
Thanks, Sandeep.